Multiply 142,857 by 2. The answer is 285,714, exactly the same digits, rotated. Multiply by 3 through 6, and they keep rotating. Multiply by 7, and every digit becomes 9. Nobody designed this trick. 1 divided by 7 forces it. We will expose the 6 remainder machine underneath the digits and discover why this ordinary fraction creates a perfect numerical cycle. This is symmetry. Let's find out why. First, let the 6 multiplications reveal exactly what needs explaining. Begin with 1 times the 6-digit block, which leaves 142,857. Twice the block gives 285,714. 3 times gives 428,571. Continue through 4, 5, and 6, and every result contains exactly the digits 1, 4, 2, 8, 5, and 7. Their order changes, but their circular order never does. Read around a ring instead of across a line, and all 6 answers become the same object with a different starting point. This is stronger than an ordinary permutation. Multiplication chooses a rotation, never a random rearrangement. Place the digits on a circle in the order 1, 4, 2, 8, 5, 7. The product by 1 starts at 1. The product by 2 starts at 2. The product by 3 starts at 4. The multipliers do not point to matching digits in numerical order. Instead, each multiplier selects a remainder state that tells us where reading begins. Once the starting digit is chosen, the other 5 are forced because the ring order is fixed. The linear answers looked unrelated only because each line was cut at a different place. Joining the 2 ends exposes the symmetry that the multiplication table was hiding. The 7th product breaks the rotation, but reveals the mechanism. 7 times 142,857 equals 999,999. Add 1, and the result becomes exactly 1 million. So the mysterious number is 1 less than a million divided by 7. Written algebraically, it is the 6-digit string of 9s divided by 7. This single identity predicts both the digits and their repetition. It also tells us the pattern is tied to a block length of 6, because 6 9s are 10 to the 6th minus 1. The rotating number is therefore built into our base 10 place value system. Now turn the 6 9s into the repeating decimal that created the number. A repeating 6-digit decimal can be written as a fraction over 6 9s. Let x equal 0.142857 repeating. Multiplying by 1 million shifts 1 complete block left, giving 142,857.142857 repeating. Subtract the original x and the infinite tails cancel. That leaves 999,999x equal to 142,857. But the number on the right is exactly the 6 9s divided by 7. Therefore, x equals 1/7. The decimal loop and the integer rotation are 2 views of the same equation. Now multiply the fraction instead of the 6-digit integer. 2/7 equals 0.285714 repeating. 3/7 begins 0.428571. Continue to 6/7, and the same block appears with 6 different starting points. This happens because multiplying 1/7 by a number from 1 through 6 cannot create a new denominator. It only chooses a different numerator over 7. The 6 possible non-zero remainder states are exactly the 6 proper fractions with denominator 7. Their decimal expansions enter one shared cycle at different positions, so the rotation table is already encoded in the family of 7ths. There is a precise reason the integer products rotate rather than merely resemble the fractions. Multiplying the repeating decimal by k gives k over 7. Because the decimal point sits before the repeating block, the first 6 digits of k over 7 are the integer k times 142,857, provided k is between 1 and 6. No carrying escapes beyond 6 digits. So the repeating decimal rotation becomes an exact finite multiplication identity. The phenomenon is not a separate curiosity pasted onto 1/7. It is the fractions period lifted into an integer by multiplying through by 6 9s. The digits are visible, but the real machine runs underneath them as remainders. Perform 1 divided by 7 using long division. 10 contains 1 7, writing the digit 1 and leaving remainder 3. Bring down a 0, 30 contains 4 7s, leaving remainder 2. 20 gives digit 2 and remainder 6. 60 gives 8 and remainder 4. 40 gives 5 and remainder 5. 50 gives 7 and remainder 1. We have returned to the starting remainder, so every later step must repeat. The visible digits 1, 4, 2, 8, 5, 7 are outputs. The hidden state sequence is 1, 3, 2, 6, 4, 5, then back to 1. That remainder orbit is the actual engine of the cycle. Each step performs the same operation. Multiply the current remainder by 10, then reduce modulo 7. Starting at 1, 10 modulo 7 is 3. 30 modulo 7 is 2. 20 modulo 7 is 6, and the orbit continues until 50 modulo 7 returns 1. There are only 6 possible non-zero remainders, and this orbit visits every one before repeating. That is why the decimal period has the maximum possible length for denominator 7, 6 digits. If the orbit returned to 1 earlier, the period would be shorter. The length of the decimal cycle is therefore the length of a modular orbit, not a mysterious property of the written digits. The same orbit can be written using powers of 10. 10 leaves remainder 3 modulo 7. 100 leaves remainder 2. 1,000 leaves remainder 6. 10,000 leaves remainder 4. 100,000 leaves remainder 5. 1 million finally leaves remainder 1. In symbols, 10 to the 6th is congruent to 1 modulo 7, and no smaller positive power of 10 has remainder 1. Subtract 1, and 10 to the 6th minus 1 must be divisible by 7. That number is 999,999, so dividing it by 7 produces the cyclic block. The wall of 6 nines and the 6-step remainder orbit are the same fact. 7 belongs to a special class, but not every prime creates a complete cycle. For a prime p other than 2 or 5, the decimal of 1 over p must repeat, and its period can never exceed p minus 1. The reason is that there are only p minus 1 non-zero remainders. 7 reaches that upper limit. Its period has 6 digits. Mathematicians call such a prime a full reptend prime or a long prime in base 10. The defining condition is that 10 has multiplicative order p minus 1 modulo p. In plain language, repeated powers of 10 must visit every non-zero remainder before returning to 1. 7 passes because its powers produce all 6 states exactly once. Compare 7 with 13. 1/13 repeats the block 076923, also 6 digits long. But 13 minus 1 is 12, so 6 is only half the maximum possible period. Multiplying 076923 by numbers from 1 through 12 does not produce one single set of 12 rotations. 17 behaves differently. 1/17 has a 16-digit period, exactly 17 minus 1, so 17 is another full reptend prime. The property depends on the denominator and the number base together. Being prime is necessary for this simple maximum length rule, but primality alone is not sufficient. The next full reptend primes in base 10 begin 7, 17, 19, 23, 29, 47, and 59. Each creates a cyclic block with p minus 1 digits, though the larger examples quickly become unwieldy to write. The important idea is not memorizing the list. It is the test. Find the smallest exponent d for which 10 to the d is congruent to 1 modulo p. If d equals p minus 1, the decimal uses the entire non-zero remainder space before closing. The cyclic number is then 10 to that power minus 1 divided by p. 142,857 is simply the smallest famous example. The same 6 digits hide another theorem when we cut the cycle into equal pieces. Split the 6-digit number into 2 equal halves, 142 and 857. Add them, and the result is 999. This is an example of Midy's theorem. For a reduced fraction with prime denominator, when its repeating period has an even number of digits, splitting that period into equal halves makes the halves add to a string of 9s. For 1/7, the 6-digit period gives 2 3-digit pieces, and therefore 3 9s. The complement is visible digit by digit. 1 plus 8 is 9, 4 plus 5 is 9, and 2 plus 7 is 9. The period can also be split into 3 equal pieces, 14, 28, and 57. Their sum is 99. Here each piece has 2 digits, so the result contains 2 nines. The arithmetic is not accidental decoration. Because the period length 6 factors as 2 times 3, the repeating block can be regrouped around powers of 100 or 1000. Those regroupings expose factors of 10 to the block length -1. Midy's pattern is the same wall of 9 seen at a different scale. The decimal cycle carries complementary structure because its numerator divides a number made entirely from 9s. We can see the half sum directly from fractions. The first half, 142, is the first 3 digits of 1/7. The second half completes the 6-digit block. Multiplying 1/7 by 1000 shifts the decimal 3 places. That shift lands halfway around the 6-state orbit, where the remainder is -1 modulo 7, meaning 6. Algebraically, 1000 is congruent to -1 modulo 7 because 1000 plus 1 equals 1001, which is 7 times 143. So the 2 halves are complements modulo 999. Their sum must be 999. Now assemble the decimal, modular, and cyclic views into one final structure. Every remarkable property now follows from one identity. 142,857 equals 10 to the 6th minus 1 divided by 7. The numerator creates a 6-digit repeating container. Division by 7 fills it with the digits of 1/7. Multiplying by 1 through 6 selects the 6 non-zero remainder states, which appear as rotations. Multiplying by 7 cancels the denominator and leaves 6 nines. Splitting the period uses factors of 6 and exposes shorter strings of 9s. What looked like several unrelated tricks is one piece of modular arithmetic viewed through decimal notation. The number is special, but it is not supernatural. There is one final twist. Change the number base and the famous digits disappear. The fraction 1/7 is the same number in every notation, but its written expansion depends on the base. In base 10, powers of 10 orbit modulo 7 and create 6 digits. In another base, repeated powers of that base may return sooner or follow a different orbit. Full reptend is therefore always a statement about a prime relative to a base. 142,857 is not an eternal string hidden inside 7. It is what the relationship between 7 and base 10 looks like when rendered as digits. The deeper lesson is that digits are outputs, not causes. A repeating decimal is generated by a finite machine of remainders. A cyclic number appears when that machine visits every non-zero state before returning. Rotating products are the visible record of where each numerator enters the same orbit. Midy's 9s reveal the symmetry halfway around it. Once the hidden state machine is exposed, the tricks become inevitable. That is what makes this number beautiful. Not that it violates ordinary arithmetic, but that ordinary arithmetic coordinates 6 different surprises with one compact rule. 1 divided by 7 writes a complete modular cycle directly onto the page. 1 fraction, 6 remainders, and a number that rotates without changing its circular order. Which cycle should we investigate next? 1/13th or 1/17th? Tell us in the comments. Thanks for watching Symmetry, where ideas are explained deeply, not dumbed down. Subscribe for the next visual proof.